Welcome to the Knowledge Graph seminar. Today, we are in the week 9 of the course, where our focus has been on what are some of the high-value use cases of knowledge graphs. Today, we have two excellent talks on how knowledge graphs are being useful in the financial industry. Pierre is going to tell us about causal knowledge graphs, and Alex and Natalia, they are going to tell us about how ontologies can be used for bankruptcy prediction. We are going to begin our session with Pierre. Pierre, over to you.
Thank you. I will share my screen. That's the first. Now I have to move a little bit that. Make sure that I do that. Almost there. All right.
We are also, yeah, perfect now. It's perfect.
Okay, so good afternoon good morning for the London attendance. I am going to talk about a special type of knowledge graphs that I've been working on for the past 5 years, which is called causal graphs. A few words on my trajectory, because I've always loved to be at the edge of research and industry. I have been in AI for quite a long time, discovered it at MIT in the late 70s. I created a company after some research at INRIA called iLog, which we introduced on NASDAQ, sold to IBM. And iLog was rules and operations research. So there was two types of reasoning systems, and we were selling general purpose technology. But in the late 90s, we had built something that looked a little bit like Protégé now, which was a tool to extract knowledge from text. And I've always been fascinated all my life by understanding how experts think. And so we have started this company 5 years ago called Causality Link. And I will talk about what we're doing and how I think it is indicative of some of the future trends of knowledge graphs. So first of all, I am going to try to be as clear as possible, having been traumatized this morning at 5 in the morning by Nobel Prizes that were dumping information too fast for symbolic AI is focused on the existing human knowledge, and it's very different than building a statistical model of the future. It's building an explicit model of the future, and we're going to spend time on that with our causal graph. Okay, the second idea is the collective intelligence, right? So collective intelligence, it has been explained very well on data in the wisdom of crowds and a lot of statistical proofs that it works, that the group IQ, the IQ of a group is higher than the IQ of any individual, but it has not been applied very well today to knowledge, that is to causal knowledge, which is what we apply, but more generally to things that are not facts, but are active reasoning elements. And so I think that a large part of the future of AI is going to be about that. That is about tapping collective knowledge of groups of people in order to build explicit models, which are not explicit models coming just from a few experts, the way expert systems were built in the 80s and 90s, but in a more automated and a more collective way. And then the last part is the importance of causal knowledge. I think there is more and more talk about the Book of Why and Julia Pearl's reasoning, which is one very partial element of causal knowledge, which is a mathematically pure, basically, explanation of causal knowledge. But I think that in general, when I look at all my history in AI, an immense fraction of the knowledge that humans derive over time to become experts is causal knowledge, is the explanation of the why. And of course, applying the wisdom of crowds by tapping collectively our causal knowledge is a fascinating endeavor. And I'm going to demonstrate what we have been able to do by applying it at scale on the financial markets. So there's two books that I strongly recommend if you are interested in that. They are rather, The Wisdom of Crowds is an easier read than the Book of Why, but they are today, I think, the books to track and to create a foundation of what I'm going to disclose. Going to causal graphs, I think it's very simple to split that into two concepts, which we call the signal and the model. The signal, it's all the things that have a time series attached to a numerical time series attached to it. And they can be the GDP of different countries, the inflation rates, the unemployment rates, foreign exchanges, all sorts of continuously varying prices for commodities, availability of these commodities, as well as all the parameters related to companies, some of them being only known per quarter, but some of them being continuously known, such as potentially demand, the positive sentiment of the market and stuff like that. This makes for rather complex nodes as far as causal graphs, as far as knowledge graphs go, because rather than having a very elementary node, we have to have something that represents the unique definition of that time series, right? So if you say, I'm interested in the revenue of Tesla, it has to be Tesla, the company, very clearly, but you can say the revenue of Tesla Model 3 in China, and then you have to track that very precise definition of the node. So one of the, let's say, efforts we have been making there has been to beef up the size of the description of the ontology that describes what is a node in a causal graph. And in large part, to be able to enable aggregation. So for example, if you have the geographic dimension for everything, you can aggregate all the sales of electric vehicles car in China and then have a time series on that, or you can aggregate all the sales of Tesla, or you can aggregate all the Model 3 across the world, or whatever, right? So the idea of aggregation as a very essential reasoning element on the nodes is very important, and I will describe that in more detail in a few minutes. The edges, on the contrary, are simpler in causal graphs than in regular knowledge graphs, because rather than being labeled by just about anything, you know, is a, has been part of, was born in, and all that, it's just saying, it's just on a single reasoning label, which is that the evolution of the signal of the driver has an impact, which can be viewed as an elasticity on the signal of the target. And so statements like the US GDP declined in 2020 due to the COVID pandemic means that the event COVID pandemic had a negative impact on the US GDP. And when you are trying to explain all the forces acting on all the financial markets, aggregating all these different statements becomes the task at hand to build automatically this very large causal graph. In some cases, by the way, the elasticity is explicit and most of the time comes from a model. So this, the second statement, every 5% increase of F150 sales creates a 10% jump in Ford's profit, comes from a Morgan Stanley financial analysis, which I am sure came from a numerical model that they had that was enabled them to generate this elasticity. And of course, our natural language processing system has to understand all that in order to understand that there is a factor 2 in the influence between the evolution of the F-150 sales, which is the best-selling truck from Ford, of which they just produced very recently an electric version called Lightning, that creates a jump in Ford's profits. So now that you have the key concept, I can go to the presentation of, okay, now if I can get that thing to do it. Okay, somehow I have a frozen PowerPoint there, no, so, okay, what is, so I'm not sure, are you seeing, yes, okay. So this is a signal, for example, that we produced for United Airlines over the course of 2020. In orange, you have the stock market price, which we just get. It's not very complex from a feed. And in blue, we have a synthetic signal that we derived from observations over time of the components of demand, employment, revenue, and I just showed that the revenue as itself, a lot of subcomponents, which are revenue, booking, sales, transaction, volume, deliveries, and all that. We have 1,700 elementary key performance indicators, such as bookings, and they are aggregated at intermediate levels, such as revenue. And then the whole set of signals that we're getting from all these different parameters is aggregated inside a single blue signal. And so here what is very fascinating is that the blue signal is dropping a good month before the stock market, and the signal is only driven by this peak of red elements. And if you clicked on, and I could do a demonstration, but if you clicked on the red bar, you would have all the text that correspond to the existence of these negative trends as stated by the journalists that we are parsing. And we're parsing 8,000 newspapers in real time in 27 languages that are automatically translated in English and parsed in English in real time. And so what is happening here, which is fascinating, is that just the signal seems to indicate that there was a very strong negative opinion on demand at a time where the US was starting to close its borders with Asia in January and February, at the beginning of February of 2020, while the stock market was reasonably oblivious of the very strong link between demand and revenue, and the drop, which is the second little peak of red bars in March, corresponds essentially to all the worries that were exposed by the airlines, including United Airlines, about their own revenue. So this is to say, here is a way to for each node in this graph to be aggregated into a kind of super node, and then to see the time series evolution of statements made in natural language processing by thousands or tens of thousands of authors, and that aggregates into sometimes a very interesting signal. The way it is aggregated, we can show it, for example, on Tesla. If we look we focus more on Tesla production. And so you can have a monthly report of all the moments where Tesla production has been talked about for every month. And Tesla production is talking about the plants, the productions, but talking about the products, and for example, talking about all the locations. And if you click on USA, you see only the cases where people are talking about the future of Tesla production in the US. And then, of course, you see the drop in March of 2020, when there was a debate between the state of California and Elon Musk on the production of the Fremont plant. So this is to indicate that aggregation across multiple dimensions, that is the companies, the locations, the industry, the segments, the products, and the KPI, is an essential element in a causal graph that otherwise is going to be extremely fragmented about links between the Germany Model 3 plant and the Shanghai Model 3 and Model Y plant. And you want to be able to aggregate at some level so that because the causal link between production and revenue, for example, do not care where the cars are being produced. So these are the nodes and an explanation of the nodes. Going to the graph, it is very fascinating that we can generate causal graphs that have this meaning of driver A influences positively or negatively target B at scale for 40,000 companies over the past 7 years. So in this case, this is a more recent NIO causal model. So NIO is a competitor of Tesla out of China. And you see that there is a very strong set of declarations in the text we parse from of a positive impact of NIO revenue to NIO stock price, with NIO revenue being forecasted to grow. And this, now you understand that this little block NIO revenue is in fact a very complex aggregation that I showed you just before of, for example, Tesla production. And that NIO revenue is supposed to grow as a positive impact, but NIO stock price is going down because it has, for example, a negative impact of the shortage of chips and stuff like that. So understanding the dynamics of a company in finance is essentially understanding all the forces that are acting on all the different nodes, and then being able to decide which of the forces are going to have the maximum impact in order to understand whether, you know, I don't know, the forecast, the positive forecast on NIO revenue is more important than its short-term negative forecast on production. The same thing can be done for countries, which is rather interesting as well, because you can see over time the evolution of a causal model for countries where the emergence, for example, in Senegal, which is a West African country, the GDP has been strongly negatively impacted by the pandemic, but there is many other factors that could have a positive impact on the GDP of Senegal, its human rights and all the parameters. And this gives a very interesting, as we think, never made before, models of all the causal forces acting on all the different parameters for all the countries in the world, as expressed by these 100 million texts that we have in our today content system. So now if we look into what can you do of these causal graphs, apart from education, clicking and getting access to all the texts that provide the very elementary information from which we derive this aggregated graph. It is possible, and I have put in the abstract a pointer to that to our scientific paper. It's possible to generate Bayesian networks. So Bayesian networks have two opposite properties. One, they are very pure mathematical artifacts that can be used to create simulations, to propagate probability distributions. However, they are DAGs, directed acyclic graphs, and therefore our causal model represents very often in finance an equilibrium. You know, the price of oil has an impact on oil demand, and oil demand has an impact on the price of oil. Well, there you can't do that, so you have to fundamentally choose the type, the strongest link in order to, from our causal knowledge graph, to generate a Bayesian network. We've worked with Alex Denef, which is a guy that has written a few books on the usage of Bayesian nets in finance, and he was the head of AI in Deloitte. In order to generate that, we have a scientific paper that has been downloaded a number of times, and I encourage you to check it if you are interested in how we can automatically generate these Bayesian networks. It is quite a feat, because normally generating a network of that size takes a few days of multiple experts to be in the same room to discuss the conditional probabilities between all these nodes, and we are able to generate that completely automatically. And then we are even able to generate over time the evolution of these graphs so that people can, for example, in macroeconomy, perceive the model changes that exist in the system that is observed. So I will finish with a few ideas on what's next, right? It's always interesting to not only say, hey, you know, we've done great things, and it's amazing that it is possible to automatically generate causal graph just from text at the level of precision at which we do that. But so what are we part of a bigger trend? And I think we're part of a number of bigger trends that I am sure smarter people are going to promote further in the future. The first biggest trend is this collective intelligence stories, that AI should not be viewed only as it is today, as a way to look at data and reinvent human knowledge. First, because it's a very convoluted way to reinvent human knowledge, but also because a lot of the human knowledge that exists is not present in the data that correspond to the decisions that have been taken by people that had this knowledge. So aggregating human knowledge at the source and being able to enable each of us to leverage more efficiently the knowledge of all these people without having to read 100 million articles in 27 languages, which is impossible, I think is a very good long-term goal for AI. And it's an AI that is going to be explainable and that is going to refer smart humans to other smart humans, as opposed to referring humans to a black box. The second part is that I am sure that causality is going to become a very important part of AI, partly because causal links are way more stable than the signal, and because they represent either natural element forces or economic forces that are not varying at the same rate than the rate at which the signal is varying. You know, the price of oil keeps moving up and down, but at the end of the day, the price of oil is linked to supply, demand, to the consumption. Demand is itself linked to the consumptions we're doing, and as we see, the green transition takes a long time and is very painful, and that makes the causal model for the consumption of oil evolve at a much lower rate than the evolution of any signal. And then we can see that very easily in medicine. There is a number of causal efforts, not many automatic generation of causal graphs, but a number of manual generation of causal graphs in medicine. And I think this is only the beginning. Of course, for us, what is even more fascinating is, and even though I'm contradicting myself slightly, causal graphs are evolving, but they are evolving slowly, but still it's very interesting to understand the temporal evolution of causal graphs. That is, how are forces moving over time, knowing that forces can exist and not be activated. If you have a driver that never moves, for example, if the price of rubber never moves, everybody knows this would have an impact if it moved on the price of on the profitability of Michelin. However, that causal link exists, but is not activated by a variation of the driver. And so the temporal evolution of causal graphs is something much more profound and interesting than the temporal evolution of each of the time series that corresponds to nodes inside this graph. And the final part I want to leave you with is my absolute fascination on how we decide collectively that some causal links are true or not. And of course, today, it's fascinating to see the theory of the Wuhan lab COVID leak sort of change completely from being a fake news or a conspiracy theory to being a potential honest cause inside a pandemic that has created such a upheaval in the world. And I think that illustrates very clearly how it is not so easy when you have very first signals of a causal link. It is not so easy to detect whether it's somebody very smart that has discovered something new or some sort of fake conspiracy theory that is going to be disregarded. And that thing can evolve over the past year and a half, the way it has done, and evolve through this collective belief that we are constructing as a civilization is very fascinating, and I think is going to be a very interesting topic for AI to apply itself in the future and help mankind evolve in the right direction. So Vinay, at that, I have finished my presentation, and I give the floor back to you. I'm going to stop sharing.
Yeah, thank you, Pierre, for that excellent presentation. So next up, we have Alex and Natalia. Alex, over to you.
All right. Hello, everybody.
Hi.
Natalia, we can't hear you.
You're muted.
Mute.
Oh, sorry. Hello, everyone. I will share my screen now to show you our presentation. Just a second. Yeah, I believe now you can see it.
Yes.
So my name is Natalia Rashinya. I'm from University of Westminster, and Dr. Boltov and I researching the ways of knowledge graph implementation. And today we will describe one of the use case we are working on, which is developing of bankruptcy prediction computational model using ontologies and graph databases, as well as machine learning engine. Today we will tell you about the main aims of our computation model. We will describe the data we use and the components of the computational model, which are ontology, graph database, and machine learning engine. And now I'm introducing Dr. Alexander Boltov, who will tell you about the generic computational model.
Okay, thanks, Natalia. So our task, first of all, is to explain the basics on which the use case is built. And therefore, I'm going to introduce the generic approach which we're developing based on the core concept of data preprocessing and analysis, which would feed the whole machinery, if you want. So as you will see in the next slide, the scheme of the generic approach involves several parts, and I'm going to describe them here. So the core of the approach is the ontology. I'm pretty sure that you've heard a lot about knowledge graphs. Well, we just heard a fantastic presentation on causal graphs. Well, ontology is also part of the graphs, as you probably know. And often we speak about ontology as the tool that structure the domain, with probably a big emphasis on what we call hierarchical relationships. Often people compare ontologies and knowledge graphs, probably sort of saying something like an allegory that if you add to ontology a dedicated data set, you sort of end up with a knowledge graph. Well, in a sense, we follow this approach. So what we want to do, we want to give the solution to the ontology creation related to the given domain, of course, and we want to go forward along this way of building the knowledge graph, but specifically realizing that knowledge graph in the form of the graph database. Why is that? Well, because we need some engine, right? So we need to make some computations that are possible in the forms of the graph database. So graph database would represent the knowledge graph, and based on this, we'll be able to construct a dedicated type of ontology that is given on the left here in 3 steps. So once it's done, so this is our generic construction, we can play our games with the graph database. And what is the essence of the game? So the idea is that we are managing the dedicated scenario of feeding the whole machinery with the selected features for the machine learning model. The machine learning model would be relevant to the type of task and data you are managing. So today we will give you one use case that would depend on the dedicated data set. We're working on different use cases. The other use case which we're working on now would involve time series, and therefore it will be a different engine to employ here. But all in all, the whole idea is that at this stage, which we call the first sort of run of the model, we feed the model with the selected features and train it. And now the call is coming. So once the training has happened, we look at the output of this procedure, and we feed it back to the graph database. Then we switch the embedded facilities, the embedded engine itself, and we want to make sure that the results of machine learning would make sense. And what are these results? Well, we expect that the features that were given as an input to the machine learning engine now would come with adjusted weights. And now this new set of features would be fed back to the graph database, and we would have another run of the internal engine with the graph database to come up with a new set of features with adjusted weights and feed it back to the model to run it again. So you see, we will expect that the model will run in some sense in several runs, and every run would ideally have a good advantage because the input to that run is going through that feedback loop mechanism. So as you will see in the next slide, there are various ways of developing the ontology, and I'm not spending too much time on this. It's a little bit of formal. I'm a logician, so I like formal definitions. So, so we just heard about dogs that were very interesting in terms of variation networks. So what we have here is the definition of the ontology in formal way is a labeled graph. Just a hint, the labeled graph is a graph with the normal concept of having a structure with vertices and edges, but then we use the language, dedicated language, to sort of label nodes here. And we do it in a quite simple fashion. What we do, we use two general parameters here, the value and the weight. And if the value and the weight are important or relevant, they work. If they're not important or irrelevant, we put them as 0. Otherwise, they would range from the given data set. So that will give us the idea how to build the sort of the targeted ontology, if you want. And it has intermediate steps. So the next slide will show you that we can actually do this in stages. First, to derive the ontology template graph, and then move to the intermediate construction where we've got a graph with values but no weights. And then we top it up with weights, and you come up with that targeted graph. So that's the idea of having the sort of formally defined ontology. And now what's happening, we want to move forward, of course, with all this construction and move to the feedback loop. You remember now, the whole idea is that we use the graph database to extract the set of features. Of course, it's the expert decision at the first instance, but once it's done, we move along the machine learning loop, waiting for the output with adjusted weights. So the weights that I adjusted are fed back to the graph database, and we switch on the engine here to shuffle the features, right? So we look at those that actually played the role, if you want, right, in the whole scenario, and they would become probably more important, informally speaking, right? Those who were not they were not very important would sort of go to the second echelon of the consideration. So this is the feedback loop in terms of machine learning. Well, we do pay attention to the data, as is seen in the next slide, and often the big data, which is a very fashionable word, which I really don't like, because everything is a big data now. That's very fashionable. Well, anyway, following the tradition, we just look at the big data and say, right, five which are on the left that are normally characterizing the big data: variety, velocity, veracity, value, and volume, would be roughly what we can see in financial data, with one exception. Volume is not important, but what is important is the relationships, right? Because financial data is such that we've got a lot of relationships. By the way, the previous talk was fantastic. It actually caught quite fundamental type of relationships, right? Those that make impact, influences. Now, what we do here, we're trying to understand more, as you will see following this talk in the next slide, what is happening in the way of building the ontology. So it's sort of a stair walk up, right, in the staircase. So we are moving on toward more and more dedicated analysis of the conceptual level of the domain, right? From the definition of the controlled vocabulary to the structured vocabulary to the single hierarchy, maybe multiple hierarchies, and ultimately we want to end up with something which is called compositional construction of classes on demand, which is a high-level analysis involving things like description logic, for example. Fantastic stuff, really interesting. Now, why do we need all that? Well, because ontology is something that would enable us to build the realization of the knowledge in form of the knowledge graph realized in the graph database. So if you look at the graph database construction, it would have several steps, starting from the transferal of the data from the ontology in the dedicated format into the graph database, technical nitty-gritty. But what is really core here is that the process of feeding the data coming from the ontology, the graph structure coming from the ontology, with the real data coming from the external sources, is the heart of the process, if you want, right? So doing that, we are able to build in stages the realization of the knowledge graph based on the ontology construction. So once we're there, we are able to move forward and look at the machine learning engine. Again, remember, I'm talking about the generic approach here. So this next slide would give you the idea, what is the machine learning engine here? Well, I'm again talking about very generic framework here. So we have the input to this framework from the graph database. The input goes through the training cycle. It then expects to give us some feature weights, which would go back to the graph database in the form of that feedback loop. And this is the essence of the scheme now, right? So the output of the graph database would adjust the next input to the learning engine. And then we go along the second loop. So that's the generic feature of the approach. Now it's to Natalia to speak about the creation of the use case based on this generic methodology.
Right. So we use this generic model to create the use cases, and one of the use cases is I will show you right now. So this is bankruptcy prediction computation model. and it's quite similar to what you have seen so far, but it is fitted with actual financial data. And speaking about the financial data we use for the testing data, we use financial records of 45 UK middle-sized private companies. And we get this information from our FAME database, which is Bureau van Dijk database. We already know the financial status of these companies. Some of them are bankrupt, some of them are not. They have stable financial positions. So we divide these 45 companies into two groups. And we receive this information from the government website, where independent auditors reports are published. Now let's speak in details about the ontology we used for this use case. It is, we call it ontology of bankruptcy prediction, or OBP ontology. And it is based on UK and international legislation. It is a set of concepts related to the bankruptcy prediction and financial analysis in general. Our OBP ontology is inspired by fiber ontology. It is a well-known ontology in finance, which is built by EDM Council, and it contains the sets of concepts related to finance and business, and also the relationships between them. And it has a more generic nature, but our ontology is focused on financial standards of financial analysis, and is also can be used as the extension to the fiber ontology, because fiber ontology doesn't contains this kind of information at the moment. We develop our OBP ontology using Protege environment, the environment that the previous speaker mentioned so far. And as you can see on the left-hand side, you can see the structure of our ontology. It's consisted of two main classes, financial data sources, which are the financial documents where the financial indicators are presented, and also financial ratios, which are actually the main input for the further component of our comprehensive model. And as you can see here, the ontology contains the definitions of these objects. Also, it contains the synonyms of these terms, which we are using as the entries, objects of the ontology. But the most important thing in the ontology, which we need to take into the account, is the relationships. So the right-hand side, you can see the hierarchical structure of our ontology. So it's subclass of relationships. And we also can define non-hierarchical relationships, and we have two types of such relationships in our ontologies to connect the financial ratios with the data in financial data sources. It's directly related and indirectly related indicators. And also you can see that it is the metadata hidden in each component. And for example, here you can see gearing financial ratio, and it contains three additional properties, which is normative value, actual value of this ratio, and weights. For creating, for using the ontology in this use case, we actually simplified our ontology and split it into two more simple ontologies, taxonomies. It's a taxonomy of financial statement elements and taxonomy of company financial ratios. And you can see on this example how they are connected to each other, and then we created this conceptual representation in Protégé environment. And here you can see the full view of our ontology, the conceptual representation of it. So once we created the ontology in Protégé environment, we save these ontologies as RDF files or all files. And in this use case, we have two separate all files. One of them contains the information from the financial records, and the second one is the ontology about the ratios of the particular of the company. So we use two types of data files for our components. It's training data and testing data. And as I mentioned before, as training data, we use a CSV file containing the financial ratios of 45 UK companies. And also we have the separate file with the output for these 45 companies, which are the bankruptcy, which is bankruptcy level. And also to test the model, we have the files with company data, particular company data. So the first file, it's actually the raw data we get from traditional database of the particular company, and we save it as CSV file. And the second one is the actual input for the machine learning engine, but it's an output for the graph database. And it contains the main financial indicators, financial features, which will be used for the analysis of bankruptcy prediction. Now let's talk about the graph database construction process. Once we had these ontology old files, we transfer these files to Neo4j environment. This is the environment we use to build graph database. And we don't need to to build this from scratch. We use the OBP ontology as the structure, the skeleton for this. So we transfer these files. We build non-hierarchical connections between these two files, as we have taxonomies. So we need to use built-in language cipher to create non-hierarchical connections between these two files. And now we have an empty graph with the node labels, and we need to get the input data for a particular company. So we use CSV file from traditional database, which contain the financial records taken from balance sheets, cash flow statement, income statement of the particular company. But before that, we need to match the labels of the nodes and the column titles of the CSV file we're using. So in future, the program, the model will know where the particular data is stated. The next step is we actually transfer the quantitative data, so the values of the particular nodes, and these values are taken from that CSV file from the company's financial records. And now we have the graph database, which is which is fed by data, but we need to calculate the ratios. The ratios are not presented in financial records of the company, and a cipher programming language allows to use built-in math formulae to calculate the particular node's values. And now our our graph is ready for feature selection, and it is ready for further component, which is machine learning engines. We save our graph as CSV file, and this is how our graph looks in a Neo4j environment. And here you can see the part of the graph, which is full graph with weights. So after first iteration, it is fed with not just with values of the components of the nodes, but also with weights, so we can arrange the feature selection. This CSV file, which is saved in Neo4j environment, serves as the input for the machine learning engine. And as machine learning engine, in this particular use case, we use classical neural network with backpropagation of errors. We use a sigmoid activation function, which is ideal for this type of data because it produces the result 0 or 1, and 0 in our case that the company is stable, and 1 is that the company has the high risk of bankruptcy. But besides the output 0 or 1, besides the results, our machine learning engine produces the weights of the features which are used in this particular iteration, and using feedback loop, we save these files, these outputs and weights as CSV files, and we transfer the CSV files to graph database. So it keeps the records of the previous iteration. It also keeps the weights of the features, and that means that it helps to raise the efficiency of the next iterations. And these weights will be used for feature selection, and that's how the noisy data will be reduced. To sum it up, we developed the generic model as well as the model of bankruptcy prediction, which contains 5 components. It is OBP ontology, graph database, feature selection component, and machine learning engine, and also raw financial data. And the main feature of this particular computation model is that it works with metadata stored in the model. It helps to raise the efficiency of the bankruptcy analysis of the company, and also it stores all the records of the company in very structured way. And what is more interesting about this particular computation model, it has the generic nature. So any ontology and any graph database and any machine learning engine can be used as the component of this particular graph database. I strongly recommend you to read the papers we published so far, and you can find the more detailed information about computational model we developed, and ontology based methodology here as well. So yeah, thank you for that, and that's it.
Thanks, Natalia and Alex, for that excellent overview of your work. Now we have 20 minutes for questions and discussions. It looks like Pierre has been prolifically answering all the questions that were posted in the chat. So that's great. There is, it seems there is one pending question for Natalia. People are asking about, is there any URI for the OBP ontology, which I believe you showed on the last slide.
Just a second. I'm trying to find this slide. Oh, sorry.
Well, so the slides are. It's
yeah,
okay. The slides are on the website, right? And you have given the references, and people can.
Yeah, I have all the references in our published papers, and also you may find my GitHub, and all the information, including the OBP ontology, is there on my GitHub. So welcome.
Right. Cool. Excellent. So, so now we are open for general questions and discussion.
There was a great set of discussions that Pierre actually answered in the Q&A. And I don't know whether it will get recorded in the video, but the two topics were temporal evolution, and the next one, which I loved, was collective intelligence from text. Maybe Pierre, can you say a few words so they can be recorded in this video about maybe collective intelligence from text?
Sure, but I'd love to talk a little bit about the delay, just to show, and maybe I'll start by that, to show the difference between finance and more mechanical things like in medicine. In medicine, when you have a human body, you can say there is a delay between one day and 3 days between the moment something goes wrong in some organ and it has an impact on another organ, right? Because this is a kind of a mechanical thing. Same thing for repairing. You know, we did a lot of expert systems in maintenance. Okay, in finance, it's very complex because there's two reasons. First, there is no underlying truth. There is no price for anything. It's all a matter of how collectively we behave and we decide a price. But also there is something called anticipations, which is if I believe that there is a causal effect that will have an impact in 10 days, I may try to play in 5 days so that I play before the others. And therefore, the whole system is self-modifying permanently in terms of delay. And information impacts the delay. So this is really nasty. All right, so collective intelligence on text. So that's how we started. We said when we got funded, we had a few very smart people that said we will only fund you if you have 40,000 texts. And now we have 100 million texts, and we keep discovering that the more text you have, and the smarter you are in terms of causal links, and not only in terms of data, but in terms of causal links. And a lot of people are saying, but so why don't you also take Twitter and Facebook? And what we discovered is by luck, we bought a content aggregator content that is paid journalists. And paid journalists have a feedback loop that they are not supposed to say anything that is too easily disproven, or they will be fired by their boss. While on Twitter and on Facebook, you can say just about anything. And most of the time, by the way, you make very outrageous statements just to be sure that you'll listen to, as opposed to trying to be smart. So collective intelligence needs a filter at the beginning so that people are honestly trying to contribute as opposed to, you know, just trying to become famous in the system. So so that's what I think is the long-term path, is trying to read from scientific text automatically, but it's a little more complex, of course, or to read from serious journalists. We get a lot of people that say, can you compare the quality of a content against another? So we wrote a little long short strategy that does that. And there are two conclusions. One is that indeed some feeds have more interesting content than others. And one of the most interesting feeds is the declarations by the CEOs at the quarterly statements, because they have a lot of legal pressure to only say the truth and to say the whole truth. If you hide a risk in your company and it is proven that you knew the risk and you have hidden it, you can get in deep trouble. So therefore, people have a tendency to overexpose the causal situation and to say the truth. But so that's the first idea, is that there is a big difference. And the second idea, and this is that the more data you have, the more content you have, the better your model. And that's rather surprising because you could say, hey, I'm adding sometimes negative content. But if you do the right filtering, including the type of optimization you have to run in order to generate a Bayesian net, you end up with basically the more collective, the smarter you are.
All right.
Thank you.
Great. Yeah. So I have a question for Alex and Natalia. I mean, the way I understood your system is at the end, you're training a neural network to do bankruptcy prediction. In that context, it's unclear to me what's the value added by the Ontology and Neo4j. I mean, they seem pretty not relevant to me. And also, your data is 45 companies, and that's that's not adequate for training a neural net. So I'm really missing what approach is here.
Right. I'll start with the data set we use. So yeah, I agree that 45 companies is quite a small data set, but we use it just to prove our theory and to use it as this explanational use case, but in future, for sure, these data sets should contain at least like the most of the companies of this industry sector to improve the database, the neural network efficiency. And what is the purpose of ontology and graph database? First of all, it structures the data, it collects it from the external sources, such as traditional database of the company, any other database, and it provides the feature selection. That is one of the initial ideas we had about using the ontology and graph database. So first of all, it's structuring of heterogeneous, connected, highly connected data, and then feature selection. Alexander, would you like to add something?
Yeah, I think so. Yes, I would like to add a little bit about the ontology. And to me, the sort of whole story is about building a structure that has sort of twofold aims, if you want, right? On the one hand, as Natalia said, yes, it structures the knowledge. It gives the sort of a good goal to fit the construction of the graph database. Well, one may ask, like, why do you need two things to do the same, right? And I think that's probably part of your question, Vinay, right? So why do you need to use both? Well, the point is that we're actually trying to bridge the gap between the sort of feeding mechanism to machine learning from the ontology through the graph database, right? So that's the core of the engine, that's the core of the technique. But on the other hand, because we got the ontology, we can switch on some formal methods here, right? So that's very important. So we can actually dive them into the top level structure of the approach. We didn't speak about that at all because
well, I mean, I think there are a lot of people out there training neural nets without using a graph database or an ontology. And so I think the spirit of the question was, okay, well, why are you not doing that? You know, why are you doing extra work?
Natalia, what to say?
Maybe I think they point to the future because of explainability. The problem is when you have a very big model and you have no idea what are the important factors. Now there is the paper I sent to you, Vinay, about Microsoft trying to explain how to explain causality in neural networks, and this is really complex. And today they say they fail. So the future is exactly what Alexander and Natalia are doing. This is a mix of both, where you have as much explainability as possible, and where you're using basically the statistics property of neural networks, where they're good at.
Exactly, so true. That was exactly on my mind. One of the main reasons is giving semantics meaning of this data. And after that, we can use this semantic methodology for the reasoning purposes, any reasoning purposes. Now we're using it for feature selection because this is the way to improve the efficiency of machine learning mechanism, a machine learning engine. But it also can be used for external analytics to structure their knowledge and to perform some reasoning on this particular data.
Okay. Well, that's fine. That's a good answer for now. So I have another question for both of you, and that is driven by this observation that hindsight is always 2020, right? So I mean, Pierre, you showed us stock price for United falling because of COVID and all that, and your bankruptcy thing is being tested on historical data. So I mean, I think we can fit things on historical data and claim success. But the real test is if we can predict what's going to happen in the future and it turns out to be true. So do you have any stories or any examples where you're not really looking at the past data, but you actually looked at the future and that future actually turned out correct in relation to your model?
Yeah, that's a really good question because right now we're working on the second use case and we using LSTM, which recognizes the time series data for financial indexes prediction. And the results we have so far, we analyze FTSE 100 index, and the model shows that it recognizes this recession of 2020. But it didn't expect such a low figure, such low values. So yes, we're working on this. We are trying to create the ontology for financial market data and financial market indexes prediction. Actually prediction, not historical data, but the future values. So yeah.
Okay. Yeah, you have any perspective on this?
But of course things are definitely more difficult if you think that what we have so far is what we can call a closed system, right? It's not an open. So we cannot say that it's open to the external signals, say, which would come and destroy everything, right? So COVID came in 2020, and no prediction would work for such a thing. So it would be good to see how the impact graph or causal graph may work here. I'm not quite serious actually now because I think the explanation and the various aspects how to make your assumptions wider, right, may come with some green light here, because we were looking at different possibilities to expand the input, maybe to have the system a little bit more open, right? See what's happening. What so far we're just trying, right? But nothing is very sort of rigorous at this stage. Put it this way.
Okay. So I have three quick answers. So the first one is, if you try to predict, to show that you're good at predicting bankruptcies on 45 companies, this is really hard, right?
Of course.
Okay, so the more serious answer is there is a theoretical and a practical answer. The theoretical answer, and this is why I'm in that business, is I strongly believe that causality is independent of the events that happen, right? So, and by the way, this is the beauty of our the elasticity model that we have, is that if something goes up, and if the sales of Ford F-150 have a double effect on the profit of Ford, if the sales go down, I can give you the negative effect prediction in a very mechanical way. So that's the theoretical answer. The practical answer is we were in a hackathon in January, driven by a professor called Sandeep Gupta, and he showed with our data that we could predict the GDP of the US 1 week before the New York Fed. And so we are not sure that this is because the New York Fed system is missing the data that we are extracting, or whether that's their nowcasting method has a delay. But what we could show is that we are better than the New York Fed with this collective intelligence of thousands of people writing, right? So I think that there is a predictability capability. More recently we had a hedge fund that said, what about the Russell 1000? So we popped 20 companies and we said, we'll see in 1 month. And they did on average 5% better their stock than the global Russell 1000. So, in 1 month, 5%, this ain't bad. But this is one data point, right? So everybody's going to say, I want to do my back testing and this and that. So the proof is in the pudding for everybody. The theory, everybody loves it, but they want to be convinced by themselves.
Okay, thank you. Thank you for those answers. Michael Nine, did you have any questions for the panel?
No, interesting applications, very interesting, but no questions from me. Thanks.
Yeah, same here, very, very interesting. And of course, there are like a lot of adversarial and game theory kind of effects. And there's one question around that in the Q&A panel right now. Any comments on that?
Oh boy.
In general, how do you?
Well, yeah.
Sorry,
given that we are nearing the end of the seminar time, maybe each of you could take 30 seconds, tell us about what's next for you, to just sort of wrap things up.
Alex, you want to start?
Sorry, the question is what's next, right?
What are you doing for next 3 months, let's just say?
Well, 30 seconds. So we're actually looking at a very interesting problem, very practical, technical problem of generating a clever machine learning model that will be able to tackle time series with multiple input. And that is not an easy thing to do, and not only because of the technical solutions, but because of how to embed it to our architecture in general, right? So that's problem number one. Problem number two, which is equally, if not more difficult, is to expand the data case to the reasonable amount of the of the data entries, if you want, right? So this is part of this research. And the third thing which my mind is working on, and it's very close to what Pierre was talking about. I've got several questions to Pierre, which I mailed to Pierre actually, because I was wondering about the mathematical properties of this causality relation, because that brought me to quite an interesting analogy of looking for the loops in such a system. That's interesting, right? So what are the properties? You've got the transitivity here, surely, because if A has an impact on B, B impact on C, etc., etc., etc. So there could be quite interesting reasoning mechanism here. But what would it give us in terms of the mathematical foundations here? So it's just sort of clicked.
Yeah, those are great problems to be thinking about.
We will solve together. Thanks.
Yeah. No, this is good. And by the way, one of the fascinating elements is no human brain. You could have a causal chain that is the result of multiple people seeing each link, but nobody seeing the whole chain. And I have an example, but we'll do that by mail, which is linked to the Chinese one road announcement and the impact on steel and the impact on the car industry in the past few years.
Okay.
So for us, we are finalizing a third version of our system. And there has been a lot of work, for example, on exchange rates. You would never believe how complex the word statements are when people talk about exchange rates. If I had known, I would not have not have been diving into it. But so once we are in it, we solved it. But that was really nasty, and quite a number of improvements on causality detection because it's very complex, and we have maybe 30 different types of causal relationships. So people are saying some link impose a negative. And I will just finish on the small example, which I love because it shows how the human brain is wired, right? So when you say American Airlines improved its profit, that means the profit went up. But when you say American Airlines improved its greenhouse gas emissions, it means they decrease their greenhouse gas emissions. So that forced us for all of our KPI to put a favorability index into the KPI so that we are able to distinguish an improvement of a negative KPI is a decrease of the KPI, an improvement. And we are naturally doing that in our brain without any missing a beat. And the poor natural language processing system is strained at the edges on things like that. But I have like maybe 200 anecdotes on that, so I will stop here.
All right. Well, I think we are pretty much out of time. I really want to thank all three of our speakers for being here, sharing their work with us, especially thanking Alex and Natalia, because it's like 2 o'clock at night. For them, they stayed up late just to participate with us live. But really thanks to all three of you for being here and telling us about the exciting work you're doing. As far as the class is concerned, we will continue next Tuesday. The next Tuesday, Naren is giving a lecture, giving us a survey of various implementation tools that can be used for building knowledge graphs. And that's a very common question we've been getting throughout the series. And that was a common question last year also. So that should be a great session on Tuesday. Thank you all very much. And we'll talk to you later.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you very much.
Bye-bye.